Hello everyone, it's Dan here. I'm gonna make a video this time instead of writing out the concepts that I want to explain. So if you guys been following my blogs in the past, in the previous two blogs, I started talking about the history of the random walk and the Brownian motion, and then I started giving a small description or brief description about what a random walk is, and the whole point of these series of blogs is to derive the Black and Scholes formula. But this time I've decided to make a video instead of writing out the concept, because the mathematics behind stochastic processes such as the random walk and the Brownian motion can be very abstract and at times difficult to understand. So I'm hoping by making guys visualize the mathematics and the process, it becomes a bit easier to understand the process. So we are still going to talk about random walks and the Brownian motion. Now, if you are a mathematician at any level, you may not enjoy this video as much, because I'm gonna simplify the maths by making certain assumptions and by skipping part of the rigorous proofs of random walks and Brownian motion. I mean, if you are a math student and you want to learn about stochastic processes, there are plenty of books out there, such as Stochastic Calculus. They're much more thorough than what this video is going to be. So if your aim is to understand the maths behind the stochastic processes, then I would suggest you guys to go to the library and borrow a book and start reading. But the aim of this video is, this video is geared towards finance students. What I want to do in this video is to explain the concept of random walks and the Brownian motion in terms of finance. Now, I keep repeating the word stochastic. It's nothing but a random variable. So if you've done any type of elementary statistics, you would have definitely come across a random variable. I'm not going to explain what a random variable is. I might give a very simple definition of what a stochastic process is. Say you have a process. So let's explain this. But in truth, what I'm saying, a stochastic process means a random variable. I'm just trying to sound smart by saying stochastic. It just sounds much better. But a stochastic process. So let's say you have a data generating function such as f of x, and this function spits out the following value. At time t, so at time 1, it spits out y1. At time 2, spits out y2, y3, and then you get to yt minus 2, yt minus 1, and you get to yt. Right? So yt is the time now. So you started the process at y1, and you got all the way to yt. The point about stochastic processes is that we have no idea what yt plus 1 is. Okay, so this observation here is not realized yet, and we have no idea what it's going to be, or any of the future values, or yt plus 2. Similarly, we don't know what yt plus 2 is, and so on and so on. So we only know everything up to yt and nothing else beyond that. So that's what we mean by a stochastic process. So what I'm going to do is I'm going to give a brief description about what I talked about last time, and then I'm going to move on into answering a question I proposed at the end of the last blog, which is why is it that we cannot predict stock prices if random walks are mean reverting? Because as I said, random walks have a constant mean. So even though they may wander off, they will eventually come back towards the mean. So if something is mean reverting, then it should be at least predictable a bit. But I'm gonna show you guys why that's not the case. Before I do that, let's just talk about what we said last time round. So last time round, I said, let's assume you're flipping a coin. So you have a coin, so flip a coin, okay? Now, if you're flipping a coin, there are two observations that you might come across. So a head or a tail. And obviously, the probability associated with a head is a half, and the probability associated with a tail is also a half. I also said, let's assign a value to each of these observations. So let's assign a value of +1 if we get a head, and a value of -1 if we end up getting a tail. So then I said, let's repeat this experiment and let's record our observations. So let's say I'm playing this game now. Okay, so I'm playing this game. I'm going to record my score here, and I'm going to have my observations here. So let's say I'm flipping this coin 5 times. So 1, 2, 3, 4, 5. Of course, we can have negative as well on our y-axis. So let's say I play this game. I flip the first time around. Let's just switch colors. So on my first flip, I get a head. Right? If I'm getting a head, I'm getting a score of +1. So I'm going to be somewhere here. Okay. I'll flip the coin again, and I get another head. So I'll add another 1 to my score. So I'll be at 2 now. So yeah, so I'll be somewhere here. I flip it again, I get another head. So 3. Then I flip, I get a tail, and then I come down to 2 because it's -1. And then maybe I get another head, and I go back to 3 on my 5th flip. Right, so that was the whole point of the last video. And then what I said was that in the limits, this random walk, this game of flipping coin, will become a Brownian motion, right? Because this game is a random walk. Now, one thing that I want you guys to realize that, and I said that in the last blog, that this is only one observation of this process. If I'm flipping a coin 5 times, I can have 32 different outcomes, right? Because the sample space that I'm looking at is just 2 to the power of my observations, right? Or omega, sorry. So in this case, it's 2 to the power of 5. I have 5 observations that I'm looking at. So I've got 32 different paths that I could take. Now, what do I mean by that? So, I mean, I could have had head, 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 tail, 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 tail. So these would have been the extreme outcomes. I could have had head, 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 tail, head, 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 tail, head, and so on. Okay, you get the point. So I could have had 30 of these, 32 different paths. So, for example, I could have had head, 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 head. Okay. I could have had tail. So I could have started from -1, right? I could have started from -1 and gone down this route. So these would have been some other. That would have been that event and that event. So let's just see how that would have looked like. So if I do head, 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 tail, then I would have had that event. Then I think you get the point, but I'll just do the last one. So then you would have had, in the next one, you would have had head, 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 tail, head, which is what we had initially. So yeah, so So these are different observations that you could have had. So if I write this a bit more mathematically, okay. I mean, I did say we're gonna look at this from a finance perspective, but we cannot avoid the maths if you want to fully understand the Brownian motion and the random walks and eventually the Black-Scholes formula. So what I said, let this score that I've got be represented by xt. Right, so this is the score I'm going to get. So this is the score. This score is just going to be the sum of the flips that I had. Right, sum of the flips. Right. So let's write this a bit formally. So xt equals to, instead of sum, I'll just use the sigma Greek letter. Right, and I'm going to represent my flips by a variable called Zn. Okay, so the sum of all my Zn's, where Zn could either take a value of positive 1 or a negative 1, with a probability of half. Okay, and where n starts from 1 and it goes all the way to capital N. Okay, so I could have n flips. I could have, so n equals to 1, that's my first flip. N equals to 2, second flip. N equals to 3, third flip, and so on until I reach n. Okay, so in our case, the capital N would have been 5 because we had 5 flips. So from the first to the fifth flip, I add up the scores, and that would be my total score. Right, that would be my xn. And then what I said in the previous video, the limit of this process is a Brownian motion. So if I write this like this, as the n goes towards infinity, so as the number of observations, as the number of flips get larger and larger, I move towards a Brownian motion. So I'll just write this out again. With the probability of half, and with the probability of half. Right? So this is a Brownian motion. A Brownian motion. And this is a symmetric random walk. So a random walk, or symmetric random walk. Let's just focus on this for a bit. I'm just going to draw out a graph to show how this works. So let's say I'm still playing this game of flipping coins. This is my xt, my score. I'm being a bit inconsistent with my notations. Maybe I should change these to xn. If that helps. I mean, it's just that I've always used a stochastic process in terms of time periods, so I'm used to the notation of t rather than n, but the meaning is the same. So if I've got my score of xn and I'm getting my observations n, so let's say I'm looking at the first observation, observation A, and I'm looking at observation B. So I flip my coin in observation A and I get a score of xa, and I flip my coin for observation B, so I get xb. Okay. Now, what I'm saying is, as the n goes towards infinity, so as these number of observations get bigger and bigger, so then I'll have observations in between these. So I'll have an observation here, I'll have an observation here, here, and here, right? So infinite amount of times. So basically what happens is I'll get different observations like this everywhere, right? I'll get different observations like that. And this process becomes a stochastic process. So if I draw the in continuous time, So if I draw the process, right, if I draw the process and start from here, it would usually look something like that, right, the typical stochastic process. And this could be Wt or Xt, however you feel comfortable about it. It makes sense when we talk about discrete times to represent it with an n, and when we talk about continuous time to represent it with a t. The way I would describe a continuous time, the way I would differentiate a continuous time from a discrete time is by thinking about a continuous time. So if you're drawing a continuous time, you would never remove your pen off the paper, right? So you would just join up the points. This is continuous. Whereas if I'm doing a discrete, I'm looking at this point, and I'm looking at this point, I'm looking at this point, I'm looking at this point. So this is discrete, this is discrete, this is continuous. Okay, so that's the difference between the two. So that's basically what we talked about in the previous blog. Now what I'm going to do is I'm going to talk about 3 things, or maybe 2. I might skip the third point, depending on how long this video becomes. But what I want to talk about is the expectation. The expectation of the random walk, right? The variance of the random walk, and the covariance of the random walk. I kind of talked about this in the previous blog. So we already said that the expectation of this in the previous blog we looked at a process where the expectation was 0. Okay, but I'm gonna define this more mathematically, and the variance is also a very important topic in this case. The covariance is sometimes ignored, even if you open up a textbook. Most of the textbooks ignore the covariance of the random walk, but I might actually show you guys this because it's very simple. So let's define a random walk. Let's define a random walk using an AR process. Actually, I did promise that this is going to be non-mathematical, so maybe not an AR process. Let's think about this from a finance perspective. But if you know what an AR process is, an autoregressive process. So you could use an autoregressive process. But what I'm going to do is I'm going to put on my finance hat and I'm going to explain what autoregressive process is. So let's assume that you ask me what the price of, let's say, Apple, for example. It seems to be very hot these days. What the price of the Apple stock is going to be. Well, simply I've got no clue, because if I did, I would not be here making a video. I'll be making millions. So I don't know what the price of Apple is going to be. So instead, what I can do is the worst I could do is I could give you today's price. So you tell me the price of Apple at t plus 1. So tomorrow, right? So we're at time t now, but you tell me to give me the price at t plus 1. So tomorrow's price. And I'll tell you I have no idea, but the best I can do is give you today's price at t. Okay. Which is not a bad guess at all, because if Apple, for example, if Apple's trading at $10, right? So that's at time t. At t plus 1, Apple could range from, let's say, $8 to $12, right? So my estimation of saying 10, okay, is not too bad. I mean, it's very unlikely that the Apple prices are going to change to $50 or go to, for example, I don't know, 1 cent. 1 cent, right? It's very unlikely. So it's very unlikely that this is going to happen. So I'm pretty much going to stay within that range. So it's not bad. But as I said, I'm not going to be exactly at 10. The price is going to change. So I'm going to have some random noise. we will have some random noise, which I will just explain this random noise by epsilon t plus 1. Now, epsilon t plus 1 is IID, independent, identically distributed, with a mean of 0 and a variance of sigma squared. Okay, and if you think about this, if you just forget about the finance for a bit, about the maths for a bit, and just think about the finance, this is confirming the efficient market hypothesis. Okay, this is confirming the efficient market hypothesis that future prices, you cannot you cannot predict future prices, and if you attempt to predict the future prices, the best you can do is give the current price, because that's all the information you have. You do not have the information for tomorrow in order to be able to say what the price is going to be tomorrow. Okay, so that is basically the definition of the efficient market hypothesis. Now, what I'm going to do is I'm going to write this. So again, this is an autoregressive process, if you're wondering about mathematics. Okay, so there's nothing complicated. This is an autoregressive process. Also, autoregressive processes are a type of stochastic processes as well. They defined, so the way you define them is you're trying to regress a stochastic process, a lagged stochastic process. So you're always looking ahead with your dependent variable, and you're looking backwards with your independent variable. So whenever you do that, you have an autoregressive process. But that's not the case. That's not very important in this case. What is important is you realizing that I could write the same process like this, right? Because again, I'm looking at one period ahead here, and I'm looking at backwards here. I'm looking backwards with my independent variable, right? So I could write yt equals to yt minus 1 plus epsilon t, or if I'm describing this in finance terms, the price today would be the price of yesterday plus some noise, right? But that noise is still an IID with a mean of 0 and variance of sigma squared. So I could repeat this thing again. So I could say the price yesterday was the price 2 days before that plus the noise. Okay, so I could do that, but then you might see that I could substitute that equation into here. Okay, so if this is equation 1, this is equation 2, I was subbing 2 into 1. So I end up getting yt equals to yt minus 2 plus epsilon t minus 1 plus epsilon t. Right? I do this step one more time, but I think after that you guys will realize what will happen. So I'll say yt minus 2 is yt minus 3 plus epsilon t minus 2. Right? So again, this is equation 3. Or let's call this one 3. So this is 3 and this is 4, and I'm going to sub 4 into 3. So I'm going to have yt equals to yt minus 3 plus epsilon t minus 2 plus epsilon t minus 1 plus epsilon t. So I end up getting that. Now, so what's happening? This is probably the most important part of this video. What's happening is I'm going, my independent variable is going back in time. So I'm not changing. I'm still explaining yt, right? In all these equations, I'm explaining yt, but I'm just transforming the model. I'm transforming the model. So I'm just expanding the model in a different way. So here I was looking at yt minus 1. Here I was looking at yt minus 2. Here I'm looking at yt, I should say minus 3, sorry, minus 3, and so on, right? But I'm adding these error terms to compensate for the lost yt's. So if I carry this process on forever, okay, this variable here is just going to go back in time. So it would go back in time to where I started. So I started this process at y0. So if I carry this on forever, eventually I'll reach y0, and that's where I started, right? Then I'm going to have a bunch of these noises here, these epsilons. So I'm going to have the sum of all of these like that, okay? And that is a random walk process. Okay, so if anyone's interested, if any of the finance students are interested in modeling random walks, this is a random walk process. A random walk. Yeah. So let's look at the expectation. As we said, we want to look at the expectation. We want to look at the variance and the covariance if we get the time. So let's talk about the expectation of this process. So let me just rewrite it out here. So yt equals to, yt equals to y naught plus sigma equals to 0 all the way to t epsilon t minus I. And so what I'm going to do is I'm going to take the expectation of yt. Okay, I'm going to take the expectation of this random walk, which is basically the expectation of y naught plus sigma I equals to 0 all the way to t epsilon t minus I. Right. Again, elementary statistics. This is a linear operator. So I would just write it out like this. Okay. Again, if you're not comfortable with these, I'll seriously suggest you going back, reading some statistics. Then I could take out this summation, so I could write it as expectation of y naught plus sigma equals I to 0 to t expected value of epsilon t minus I. All right. Now let's pause for a second, because it's not very difficult now. It's just reviewing what we said. I said that these error terms over here are IID with a mean of 0, with an expectation of 0. So if the expectation of this process is 0, of these error terms are zeros, this would be 0, right? So 0 times the summation of these is 0. So all I'm left with is the expected value of y, expectation of y naught. Where y naught is just a number. That's where I started from. So yes, the expectation of any number, the mean of any number, the average of any number is just a number. So let's call that number mu. Right? Let's call that number mu. So what I'm saying is this. I've got time and I've got the stock price of Apple. Let's just call it YT to stay consistent. YT. And what I'm doing is I'm starting from this value here, y naught. Okay. And I have the mean of mu here. And what's happening with this stochastic process is that it's mean reverting. Right? This is what's happening with my stochastic process. Right? It's mean, it's got a constant mean, which is very rare. And I kind of said that in the previous book. Now, what I said in the last part of the previous book was, why can we not predict prices? Because if I know I'm here at this point with the price, I know that it's going to fall down, so I'm just going to sell this stock. And if I know that I'm here, then I know it's going to go back up somewhere, so I'm just going to buy this stock. So yeah, I can make nice profit out of this trading strategy. But let's see why these prices are not predictable. Let's take the variance of the random walk. So the variance of the random walk would be the variance of y naught plus sigma equals to 0 t epsilon t minus I. Simple as that. Again, this is a linear operator. So variance of y naught plus the variance of sigma I equals to 0 all the way to t epsilon t minus I, and again I can take out the summation, so variance of y naught plus sigma I equals to 0 to t, the variance of epsilon t minus I. Right. Let's pause for a second. Again, so we said y naught is just a number where I started from, where I start this process from. Okay, so this number cannot have a variance. The variance of this number is 0. Right? So any number, I mean, a number cannot have a volatility. So variance of 5 is 0. Variance of 10 is 0. Variance of a million is 0. So y naught is just another number. So that's 0. Let's look at the other part, the second part of it. I said the variance of this noise is sigma squared. Okay, so what I have is sigma I equals to 0 t sigma squared, but I've got t of these sigma squared, so I've got t sigma squared, right, because I have the sum of these sigma squareds. Yeah. So let's partially analyze what that means. In simple terms, what this means is that the variance of my process or of the random walk is growing with time. So as time goes on, the variance grows. Now it's easier to visualize it. So t again and yt. So I could have this constant mean over here, and I start from y naught. But basically what happens is that I start, so maybe I get a process like this. I could get a process like this, okay, which is growing with time. So if you see this process over here is growing with time, okay. Or I could also get a process that looks like this, which is even harder to predict. This one over here is volatility cluster. We can model that using Garch or Arch models. Okay, this one over here is a bit worse. So I've got this constant mean, and what I could have is so yt here and t here. So I start from y naught again, and my process starts to go up like that maybe. Okay, and it could go on like that forever, but it doesn't mean that it's not mean reverting. Maybe somewhere along here it starts to go back down. Okay, so I don't know. So the mean reversion here is a bit easier to see, but here, so this resembles stock prices a bit more. So it's more realistic. This is probably what you would see with stock prices. So they go up and then they go down and then they just move towards the mean. So with this kind of a process, it's very hard to see where the direction of the price is going. So I cannot make any predictions. I mean, clearly the price could go down as well as up. So maybe they go up like that for a bit, and then they go constant, and they go back up, and they're moving towards the average, the cost average, they go down a bit. So you understand what's happening. So because the variance is not constant, this is why I cannot predict a random walk, and this is why we cannot predict prices. Now, I'm going to talk about the covariance just a bit, but just to clarify, you want the variance to not be a function of time. You don't want that. So you don't want it to be a function of t, right? And or another way to think about it, you want the variance to be less than. You want the variance to be less than infinity, right? You want a finite variance, not an infinite variance. So having said that, let's deal with the covariance of yt and yt plus h, for example. And just to keep the maths simple, I'm going to assume that h equals to 1. So I'm just going to look at the covariance of yt with yt plus 1. Okay. Now, what I'm going to do is I'm going to use this equation here. I think it's an equation. Well, we're going to give it a number, but I'm going to use this equation, this one over here, yeah, to write yt plus 1. So what I'm going to do is I'm going to say covariance of yt, and it's going to be yt plus epsilon t plus 1. Now, is there a linear association between yt and yt? Of course there is. So I've got covariance of yt with yt. Is there a linear association with yt and epsilon t plus 1? There is not. So the covariance of yt and yt plus 1 is just the covariance of yt with yt. Now we know that the covariance of two similar variables, or two variables of the same nature, is just its variance. So I'm just looking at the variance of yt, which again, as we saw just here, the variance of yt is t sigma squared. So this is t sigma squared. So even the covariance is growing with time. So we don't want it to be. We don't want it to be. So this is what we don't want. This is what we don't want. This is what it is. It is growing with time, but we don't want it to be growing with time. What we want it to be doing is to grow. As a function of h. So we want it to grow as a function of h, not as a function of time. But this, I don't know why, but this third criteria is always skipped in majority of the textbooks. It's a bit more. I guess it's a bit more abstract to explain. I mean, it's very hard to visualize. I don't have a graph for this one, so it's very hard to visualize it. So you just have to understand the process. But these three things that I talked about: the expectation of yt, the variance of yt, and the covariance of yt with yt plus h. These are what we call these are the criteria for stationarity. And essentially, if you ever look at a mathematical process that is not stationary, then you cannot predict that process. There's no way you will be able to predict that kind of a process, right? So if it's non-stationary, I don't know if I made a mistake here, but let me just repeat that. If the process is non-stationary, then you will not be able to predict the prices. Okay. So in order to make a prediction, you want the process to be stationary. The random walk was stationary in mean, it was not stationary in variance, and it was not stationary in covariance. You can think of stationary as being constant. So you want these three variables to be constant. The mean was constant, the variance was not constant because it was growing with time, and the covariance was not constant because it was growing with time as well. So, which is why if you think about it, so I'm sure pretty much majority of the people have heard of the CAPM model. Right? If you haven't, it's the capital asset pricing model, which basically says, or it claims that it could predict prices, but it doesn't. CAPM does not predict prices. CAPM predicts returns. Right? The reason why it cannot predict the prices is because these processes, such as random walk and Brownian motions, are non-stationary. That's all for now. If I do another video, it will probably be on the properties of the Brownian motion. I will talk about stationary increments, and also its the properties of the Brownian motion, which is that it's non-differentiable. So if you guys think that this video was useful and you want me to explain these two concepts in another video, then do let me know. Thank you for watching.